Very much, Duan and Rajesh, for the invitation. It's my first time in the Cornada, and it's the best time because next lecture in the Cornada we will be hosting next year. So this is the last talk, and the next talk next year we will be hosting. So that's a very good time and the perfect time for my talk, in my opinion. Yeah. So thanks again, Rajesh and Duan. So topic of the talk is the monotonicity principle for quasi-linear conductivity inverse problems. It's a joint work with an amazing team from Italy, the Antonio Corvo, Luisa Faella, Gianpaolo, and Antonella Tamburi. So this all work started in 2019-20, yeah, and after that, lots of water has been flow under the bridge. But I prefer to talk on this topic because of many reasons, keeping the audience in mind, first of all, and the second thing is that this is the work actually is the extension of, in some sense, to the work which we were eager to do, especially with the Rajesh. We were looking for some non-linear setup and homogenization. And when I was in Italy in January, December of that year, eventually the work proposed by the inverse problem for the quasi-linear setup. And that sounds interesting to me because earlier I used to work in the inverse problem using the topological derivatives and things like that. And we were looking for some tool to deal the non-linear problem easily. So let's just start with the three. So this talk will have three parts. So first of all, as you can all have seen in the lots of talks in this Cornada, we have seen many people talked about the inverse problem. In fact, this Cornada started with the inverse problem. So this topic attracts the attraction of engineers, physicists, mathematicians, and lots of people from different areas and sub areas. Yeah, so we will see first of all the three. This talk will be divided into three parts. First of all, we will see what is inverse problem, and we will try to understand the inverse problem, in particular in this topic of the conductivity or nonlinear conductivity. And then we will see monotonicity principle, which was developed to deal with the inverse problems, and that was bit different than the classical methods already existing. And then in the third part, we will see the quasi-linear setup, and we will see how the monotonicity was adapted for the quasi-linear setup, and how this lead to a non-iterative algorithm to develop, and which became quite impressive in the terms of results produced. So in general terms, we have seen many times this thing in this Cornada, that the inverse problem is something like you have a domain omega, and you have some anomaly inside V, and we don't know what is the size and what is the shape and where it is, this anomaly. But we cannot enter inside the domain. We have to just deal with the boundary data. We can send signals from the boundary, and we can receive the signals from the boundary, and try to guess or reconstruct the shape of the anomaly, which is V. Okay, so in this particular setup of the electricity, we will send some voltage through the boundary, through the electrodes, which is figured out here in the and then we will receive the current flow outside through the same nodes, and then we will analyze this current and try to develop an algorithm which can help us to reconstruct the anomaly V, which is inside. We don't know the shape, and we don't know the position, nor we know the size. Okay, so here I will denote by omega the region of the conducting material. Sigma I will represent by the nonlinear electric conductivity, and E is the electric field. So if you see domain, there are two conductivities, sigma I for the phase 2 and sigma B for the phase 1. Okay, and I1, I2, IM represents the current which is going outward, and then normally, and then we will send the voltage which I denoted in the model with F here. So we have J, is the electric current density, which is equal to sigma and the conductivity times the electric field. So if there is no source inside, so from the Ohm's law, and if we apply the F voltage from boundary voltage F, for the linear case, we have this model. Divergence of sigma gradient U is equal to 0 in omega, and U is equal to F on the boundary, where F belongs to the proper space for the well-definedness of the problem. Okay, and from it is very for this particular linear setup, it is very well known in the literature that U is the solution of this minimization of Dirichlet energy. So here we have Dirichlet energy denoted by F sigma, and F sigma is integral over omega conductivity times the norm of gradient of U squared. And this is well known, and this needs typical techniques of calculus of variations. We can show that the minimum of this energy functional actually is the unique solution of the PD post above. Okay, so here we have to notice that F is the voltage we are sending in, we are applying on through the boundary, and then what we receive is this current density normally, which is going out, that is sigma and times normal derivative of U. Okay, so here we have a map, delta sigma, which maps the voltage applied through, which maps the voltage applied to the current coming out through the boundary. And basically, this is called the Dirichlet to Neumann DTN operator, and this is a very interesting tool to solve the inverse problem, which I mentioned in the first part of the talk. Okay, so now it is clear for the example of linear case what we are trying to do. We have a domain omega, we have anomaly V, we are applying the voltage on the outside boundary, and we are measuring actually the outflow of the current, and then we develop algorithm to find out the size and the position of the anomaly V. So definitely there are many methods: iterative method, non-iterative method, and these are the two areas which deals with such type of algorithms. So of course there is iterative method. There are lots of, and the iterative methods are very got very bad name because of the production cost. Its computational cost is very high. So non-iterative methods are difficult, but they got a very good name because of the so there are lots of non-iterative methods like linear sampling. One of the oldest linear sampling method, the famous guys, the Colton and all, made it happen in '95, and then the latter factorization method with Kirsch in '98, and then enclosure methods for Ikeata in '99, and then multiple signal classification, which is named as music method by Devaney in 2000. And later in 2002, it was developed by one of the co-authors, Antonello Tamburino, and actually he used this DTN idea to develop the algorithm using monotonicity. Yeah, and then it was a non-iterative methods, and it was in the category of non-iterative method. And the idea which I will explain in the later part of the talk was used to develop this algorithm, and it was quite successful. So general comparison between it, one of the non-iterative method which I also used to study. I also study now. That is called topological derivative method. But there we were not able to deal. We did not deal. I'm not saying that it is not possible to deal, but we did not deal with the non-linear problems or problem with some non-linearity. So when this monotonic principle method was proposed, the first idea of ours was to attack some problems with nonlinearity. Yeah, and so below I am just categorizing the two major characteristics of these two methods. So computational cost for iterative method is high, non-iterative method is low. Recovered information is complete or full construction for the iterative methods, and the partial for the non-iterative. A prior information is strongly needed for strong information is needed, and for non-iterative it's very little. Input data is few for the iterative methods, and for non-iterative methods we need lots of input data. Okay, so let's start with the monotonicity principle. So monotonicity principle in 1990, first that Gisser-Isaac Novel has showed that if the conductivity sigma for the one material is less than equal to the for another material tau, is implies that the DTN sigma delta sigma is less than equal to delta tau. Okay, and what happened? Definitely here sigma and tau is the conductivity, and sigma delta sigma and delta tau are the DTN operators. Okay, so as we noticed before in the first few slides that delta sigma and delta tau are the operator which was measuring the outflow of the current. So so basically this inequality says that if conductivity is sigma is less than equal to conductivity of tau, then the outflow current will respect this inequality. Okay, so taking this thing in account, this Antonello Tamburini and Rubinacci, they in 2002 converted this idea to develop the non-iterative algorithm, imaging algorithm. So what they said, let's take the contrapositive part of this result and use delta sigma. If the current flow does not respect this inequality, implies that the conductivity of the material inside also will not respect this inequality. It means if you have delta sigma not less than equal to delta tau, it will imply that sigma is not less than tau. How they use this information? This contrapositive of the result of 1990, they said that we will put the test anomalies, okay? And if the test anomaly is subset of the anomaly which is inside, which we don't know, then delta sigma tau will be greater than equal to delta sigma v. Okay, so the algorithm which were developed that used this information. The information was exactly which is shown in this figure. They consider first of all the many different T and start trying to examine the out current flow at the boundary. So if the test anomaly was inside the V, then they were getting that according to the paper of 1990, they were getting this. But you see here, obviously the computational cost is low because they are not solving the PD again and again. They are just comparing the boundary current flow, the outside flow of the current. That's all. So what they did lots of they put lots of test anomalies and started comparing the outflow of the current. So and they use contrapositive of the inequality proposed in that paper. So as soon as the outflow of the current we are not greater than equal to, for example, which I am mentioning here, that delta sigma t is not greater than equal to delta sigma v. It means outside current flow with respect to the test anomaly is not greater than equal to the delta outside current flow with respect to sigma v, it implies T is not the subset of V, which is the basis of the imaging method based on monotonicity principle. In fact, here we have two options. If delta sigma T is not greater than or equal to delta sigma V, then we have two options. Either T is outside of the anomaly, the test anomaly is outside of the anomaly side, or test anomaly is intersecting the anomaly inside. So it is equivalent to if we change the role of test anomaly T and V in the right hand side figure. If the test anomaly is some sort of change the role of the anomaly V, which is the real anomaly, then this same information delta sigma T not greater than or equal to delta sigma V will give us two options. T is intercepting and V is outside. So in this case, based on this, they developed this algorithm. So they considered all the possible test sets, the union of all the possible test sets for which the outside current flow delta sigma Tj is greater than or equal to delta sigma J. Delta sigma J is the data which we are collecting at the boundary for the real anomaly, and delta sigma Tj is the outside current flow for the test anomaly. So if we take all the anomalies which is either intercepting or away from the real anomaly, and if we take all the union of this, okay, so if we take all the union of this, then we will get the we can deconstruct the anomaly inside, which is the original anomaly. So equivalently, if we this algorithm is equivalent to consider another set V of, for example, Vu is equal to intersection of all Tj's, such that delta sigma Tj is less than equal to delta sigma V. In this case, we take the intersection of all the tests where anomaly is inside the test anomaly. Okay, so these two, the second one which I did not write here, but that is equivalent to the algorithm which is already written here. Okay, and for the results in the book, in the paper of Tamboroni Ragunachi in 2002 and Harak and Ulrich in 2015, they produced some result, and it is clearly visible from these three experiments that monotonicity method was functioning really better than the factorization method and the imaging method. Okay, so let's see. So far it is clear to us what is the inverse problem and what is the monotonicity principle, what is the algorithm. Now let's go to the mathematical part of the real mathematical part. It mean to say the pure mathematical part of this research. So as I indicated before, for the linear case or the stationary currents, we have current density is equal to sigma times Ex. Then where sigma is the constant for the stationary version. Then for the linear case, we have sigma, the current density is equal to sigma, the conductivity times E, and both will depend upon X. So for the P-Laplacian case, your J is defined with sigma X and then norm of Ex times P power P minus 2 and Ex. So this linear case was explored by Calderon in 1980. Then we found when we were dealing with this the below case, quasi-linear case Jx, and where the constitutive relationship is that where your sigma has some nonlinear contribution from the electric field E. Okay, so when we were dealing with this paper, which appeared in the inverse problem in last year, So we found that up to P Laplacian, it was possible to use the classical DTN operators, and then after that the problem started. For example, if in place of linear case, if you take the algebraic combination of 2, 3, 4. Maybe different powers of sigma and E, then the classical operator does not work, which even was working for the P Laplacian case. Okay, so we will focus in the quasi-linear case where this electric current density has this format sigma x E norm of Ex times Ex. Okay, so in this case, our model problem will look like this: divergence of sigma x with the modulus of gradient ux, and gradient ux is equal to 0. And from through the boundary, we will be applying the voltage F. So the first part, we applied the techniques of calculus of variation, and we showed that definitely we have some hypothesis for the conductivity sigma. Yeah, and for those hypotheses, which is very general, which I will mention in the latter part of the talk, we found that the unique solution of this problem is actually the minimizer of this F sigma, where F sigma is actually the integration of the Dirichlet energy density, which is Q sigma, and which is where Q sigma is defined by with the help of integration 0 to E sigma x xi dz for all z for all E greater than equal to 0. And in this case, our DTN operator was mapping F to the current, and the current here is like sigma with x and modulus of gradient of u times the normal derivative of u through the boundary. Okay, so if we have these two assumptions here for P greater than equal to 2. Okay, on conductivity. So here, if you see, conductivity has two bounds, and if we draw that in the figure, it will be this. Any sigma is permitted between these two lines, where upper bound is coming with the constant sigma 2 bar, maximum of 1 and E by E0, P minus 2. And the lower bound is coming from another constant multiplied by E by E0 by P minus 2. So this assumption is valid for P greater than equal to 2. Yeah, but I just want to inform all of you that P less than 2 is also almost done, and that will be the future work. We did not submitted it yet, but the work is it looks like it is done. We are fine with it. Okay, so that also, so if you observe, if you really go through the articles and the papers on this topic, if you can find that these two assumptions are the quite general assumption. It's we are trying to cover almost every single cases, practical cases through these two assumptions. Okay, so here we observe that if sigma is less than equal to T, okay, sigma is less than equal to T, then this energy, the Dirichlet energy of UF, F composite, it means F sigma of UF. UF is the solution of the model problem when F voltage is applied is less than is respecting the inequality of the conductivity. Okay, so is sigma is less than equal to tau? Yeah.
I have like 5 minutes, so if you want to leave some time for questions. Yeah.
I will just show the main results and then I will leave for questions. Okay, just 2 minutes more. Okay, I will just show the main result. So so this result actually that energy, the Dirichlet energy was respecting the inequality of tau appeared in the last main result. what is happening in the main result? We found that sigma is less than tau. It implies that the current flow, average current flow, this time is not the flow, only the electric current flow outside. It's actually the average current flow through the, this average current flow respects the conductivity inequality. So now the natural question arises that we all started the discussion by saying that we will apply the voltage, we will measure the current, and then we will try to construct or reconstruct the anomaly. But here, what is happening that in place of current, we are getting average current. So from practical point of view or physical interpretation of the average chain operator is that in place of eventual calculation, we have to supply the voltage for the time 0 to t, and then we have to measure the outside electric flow for the same time period. And so it will not be eventual, but it will be like a process to supply the voltage and then correct the. And in this case, of course, since we are dealing with the Quasi-linear, the computation, the operation cost will be a bit higher, but still notice it is still better than iterative algorithm, because we are not solving the problem like iterative case in each iteration. We are just calculating the average electric flow through the boundary, and then we are taking the fit for average of between the time 0 and t. Okay, so here I quickly mention some references and then I stop for the questions. So the first time it was, so all the references which I'm mentioning here is mentioned before, and one of the very important paper which gave us the clue was the paper with Saulo and Zhang. This is the paper deals with the P-Laplacian model, and here we observe that the classical analysis will not work for the Quasi-linear case. Yeah, so I stop here, and if there is any questions, please. Thank you for your attention.
Yeah, thank you, Ravi, for the nice talk. So it looks like there's a lot to be done. So if there are any questions, please.
There are lots, a lot has been done, and there are lots to be done as well. Yeah, please, I'm here. I'm all here for the question.
Yeah, so if no one else has, I have a few comments. So the description you gave of the monotonicity principle. So finally, meaning based on that, you have this algorithm, but it seems to be applied in a heuristic way. Is there, meaning it's like, I don't know, I have this impression that you can make a mesh, and then you see if cells of the mesh are included or not using the test which you have on the lambda sigma, and then from that you can reconstruct. But for that you need to have some estimation of the size of the anomaly to begin with, to start with a reasonable mesh size, no?
No. Because you see, if the test is away from the anomaly, it does not satisfy the inequality. It is not greater than equal to. Okay. So once it is not satisfying, you can keep the size bigger and take the test anomaly to the other part of the domain. Okay. So that's what this algorithm
okay, I think
says.
there is another question by Duan.
Yeah. Please.
So is this being implemented in actual measurements, and can it be compared its efficiency against other methods?
In this article of inverse form, no. But in the next articles, we are trying to include some numerics. Yes.
And how, so I missed the dependence on the, of the results on the regularity of the domain. What are the hypotheses on the domain? Can it have corners?
So I told you that the applied voltage, right? Applied voltage belongs to some space, right? So that depends upon which type of boundary we have, right? So if you want to look for the corners, right, then we lose the C1 type of boundary, right? So then itself, existence of the solution needs lots of regularity for the boundary data, no, for the voltage applied, right? So it all depends upon which space is considered, and accordingly what voltage, which space we have the voltage applied.
It's because thinking of applications, I suppose that sometimes you would like to consider edges, and even
Yes.
if you don't, even if you can't prove existence completely rigorously, if you take existence of solutions as hypothesis, would you still have the monotonicity of the Dirichlet-Neumann?
If you want to forget about the idea of convex monotonicity comes from the Gattau derivative of this Dirichlet energy. So if you can calculate mathematically with the minimum hypotheses, it's all fine. But at least you will get the monotonicity of the delta. This part actually I could not present because I was not left with the time. So this is the main part of the quasi-linear case. When we have the non-linearity with this, we have some difficulty in comparison to the P Laplacian in the linear case. So in this, for this we have to calculate for establish the monotonicity. We have to calculate the Gattau derivative, which was not needed for the earlier cases.
And do you, so the result is still valid when you have many anomalies? So this set capital V, does it have to be connected?
Yes, then of course we have, in that case we have to divide the algorithm in subparts. Because if you have for example two disconnected components, okay, two components inside then your T may contain one but may intercept other, correct? So in that case we will have to think about dividing the algorithm in many subparts.
But the monotonicity of the Dirichlet-Neumann would still hold. So if V is not, if V has two pieces, if V is V1 union V2, is it still true that if the test region contains both of them, then the lambdas will be monotone?
Yes.
Is it still true?
Yeah, this is true. That is true.
Okay.
Yes. Yes.
Okay, thank you. Thank you, Ravi.
Yeah.
Yeah, so con esto llega a fin en nuestras sesiones sobre cálculo de variaciones. Gracias a todos que participaron y contribuyeron, y también los oyentes. Y también gracias.
I have one question. Are we recording?